Do you see my screen?
Yeah, perfect.
Okay. First of all, thanks for the invitation to the organizers. It's very exciting for me to be speaking in this nice forum. There has been a lot of very cool solutions that I didn't know about, and I'm happy to introduce some ideas of the work that we are doing as part of Bitmap. I will talk today about how we use digital tools to promote research standards. First, a bit about myself. I'm a postdoctoral researcher at the Technical University of Denmark. And part of my job there is to contribute to the development of a battery ontology, and also more recently joining the European Materials Modeling Council to develop a characterization ontology. And this is all work ongoing. First, a bit about Bitmap, which stands for Battery Interface Genome Materials Acceleration Platform. And it's a large European project aiming to accelerate the discovery of disruptive battery materials, doing so by integrating experiments, simulations, and artificial intelligence. One of the main goals is to demonstrate the workflows where an experimental activity can trigger a simulation and vice versa, all done autonomously. And this morning, Helge Stein gave a nice overview about how he's doing that in his lab using the HELAO framework. To achieve this, this is a topic that has been touched many times throughout this workshop, but essentially we need to upgrade current research practices into increasingly digitalized paradigms. In the classical way of doing research, users draft procedures, they carry out experiments, they gather and analyze results, compose publications, and store all data, hopefully. And each lab in its own way, usually each person in its own way. However, if you want to guarantee interoperability, we need to upgrade current research practices into machine-readable versions if we actually want to enjoy the benefits of using information systems. But more concretely, what are the benefits? So for one, if we use standard operating procedures and structured metadata, we can improve reproducibility of our experiments and activities in general. And this is especially important when doing battery research. This is one of the main points of this field, the reproducibility crisis. Moreover, by representing experimental procedures as workflows, we can take a step closer towards integrating simulation, experiments, and AI all within the same framework. We can just modularly put them together. Structured data is, of course, key to achieve the reusability and interoperability aspects of the FAIR data principles. And ideally, we will communicate science and the understanding that we gain from our research activities using clear common vocabularies with clear concepts, defined terms, and ideally we will have quick access to commonly used definitions, such that we can facilitate transmission of knowledge. Last, and probably more importantly, if we store data with additional context provided, for example, by an ontology, we can upgrade simple data into linked data, which not only humans can understand better, but also it can be dealt with, queried, searched, and used more efficiently by machines. So in Bitmap, a large breadth of researchers have agreed on abiding by key standards to promote reproducibility and interoperability within the project. These standards include procedures for testing batteries, requirements for reporting experiments, simulation activities, and data modeling, and also materials with key specifications that are agreed to be used throughout the consortium. However, if they stay simply as static documents, they are unlikely to be adopted if they are just stored as lengthy reports in PDF format or Excel files. Once agreed, what would be the best way to implement these standards project-wide? And our approach is to use laboratory notebooks to do that. We have developed an online laboratory notebook as a way to implement standards. Effectively, the OLN digitalizes standards as web forms, which are filled by the user when reporting experiments. From the front-end side, the users are exposed to the structural way of reporting data that is being set by the standards. So users are encouraged to comply with good reporting practices, but at the same time, in the back end, the submissions themselves represent machine-readable entries of metadata that can be stored and easily queried in a database. In parallel, we are developing a battery interface ontology called BATinfo in order to promote the use of a common vocabulary for humans and facilitating the access of data by machines. BATinfo is a domain ontology based on the elemental multi-perspective materials ontology MO, and we have planned a first release of the ontology on February 28, open to all the scientific community. But coming back to the beginning, what is exactly an ontology? And in short, I like to think of an ontology as a machine-readable representation of data. In BATinfo represents, as part of this ontology, battery knowledge is represented as a network of concepts connected by a predefined set of relationships. Each concept has definitions, synonyms, properties and attributes, but they have been adopted by authoritative sources like ISO, EIC, and UPAC. Edges describe relationships between concepts, such as parenthood. For example, electrolyte has part charge carrier ion, and also hierarchies. For example, solid electrolyte is an electrolyte. But it's not only limited to this type of relationships. There are more complex relationships that are based on logic that can be processed by computers. However, by itself, BATinfo is encoded as a file written in ontological language, usually OWL. It's essentially a backend tool. So the question remains how the user can concretely benefit from an ontology. One way that we have devised to do this is to use, again, the OLN as a vehicle to integrate BATinfo ontology. We would like to stress that the OLN is a primary point of interaction between the information system, in other words, everything that is in the back end, standards, databases, ontologies, and the user. In that way, we can expose the user through the OLN to the ontology by enriching the interface that the user sees. For instance, we can use metadata for the metadata keys, the names in the form. We can use them to be compliant with the names that we use in BATinfo, such that users know that that's the correct term to refine to that concept. We also provide help functionality for the fields, such that the user can not only check what type of information he needs to input, whether it's a number, it's a string, or what are the units, but also the definitions of the field that he's dealing with, such that he's already exposed to these definitions that have been canonically defined for the ontology. In addition, we also provide hyperlinks to other media like OntoWiki, which is a Wikipedia-style page where users can explore definitions and relationships that are inherited from an ontology. In the back end, each metadata entry can be tagged with an ontological concept, such that the metadata not only it's alone by itself, but it also contains pointers to the ontology that provide context on, for example, what material has been used, what are the methods that have been used, the procedures, electrochemical models, the part of the battery that has been characterized, and so on. Sorry, just to finish with this slide, having metadata labeled with ontological concepts can unlock the power of linked data and semantic search for find resources. So as a take-home message, we believe that we can leverage the role of the OLN as a primary point of interaction with the user. First, as a way to encourage users to comply with reporting standards by implementing these standards as digital forms. Second, it enables to store metadata in the machine-readable format. Third, it exposes the user to common vocabulary, definitions, and elucidations from authoritative sources through the integration with ontology. And fourth, it enables integrating metadata with semantical information and move towards increasingly towards a more digitalized paradigm of storing data. In other words, a knowledge base. With that, I would like to end thanking my collaborators in SIMTEF, in University of Picardie, Jules Verne, Collège de France, and all of you for your attention. And